नमस्तुभ्यं वरदे कामरूपिणी विद्यारम्भं करिष्यामि सिद्धिर्भवतु मे सदा पद्मपत्रविशालाक्षी पद्मकेसरवर्णिनी नित्यं पद्मालयां देवी सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा।
Very good evening to all of you. I am Dr. Richa Kothari and welcome to our ongoing ISCI Physics webinar series. We recently concluded last month our MRI series and now we are starting with CT. So today I welcome our speaker, Dr. Nilay Nimbalkar, who is the Director of Precision Scan Center in Nagpur and also in charge of the CT and MRI of 7-Star Hospital in Nagpur. He is a very excellent teacher. He's involved in a lot of publications and very active in all, not just academic, but also social activities. So we hope to have a very interacting and rousing session today. The moderator with us today is Dr. Hemant Telkar. He's the president of IACI, this thing, and he is one of the pioneers of cardiac imaging in India. Welcome, sir. And Nilay will be talking on history and basic CT physics today. Over to you, Nilay.
Yeah, welcome, Nilay. And I think one thing to add that he's also an examiner and a teacher for the CPSC program, and that's how I end up getting Nagpur's orange burfi every year when he comes. Incidentally, the CPS is just very close to my setup, so we end up meeting there. Nilay, welcome. A strong, dynamic team member of IACA. And as ICA move forwards, you will find people like Nilay and Richa being sitting on the chairs where we were sitting. Best of luck, Nilay. Proceed with your talk.
Thank you very much. Am I audible? I see. I will just share my screen. Is it seen, sir?
Yes, absolutely.
Okay, fine. Thank you very much, Dr. Reach and Dr. Hemant sir, for the wonderful introduction. And definitely, I will be with you people there, sitting adjacent to you, and you will be always our mentor and there to guide us. And thanks for the introduction. And we will come to our today's topic, the history and basic physics. I'm Dr. Nilay Nimbalkar from Precision Scan and Research Center, Nagpur, representing the Center of India from the very basic center city of India. So everything should start with the history, as we always go with our patients, that whenever we are handling our patients, we go ahead with the history first, and then we proceed with its dissection, with its medication, and with its treatment. So whenever we are going ahead with the history, the same is true with the CT scan, because it is really important to know what our ancestors have done to give us such a wonderful CT, such a wonderful modality to go ahead with scanning, and made a bread and butter for all of us. So it all started in 1917, when Australian mathematician J. Redon, while working with gravitational theory, put forward that 2 or 3 dimensional objects can be produced from infinite sets of all its projections. So if you have multiple projections of an object taken from different directions, if you can combine them, then you can recreate that object in the form of an image or in the form of a model. So this theory was taken up by Mr. J. Redon in 1970. He had those theorems as well as all the algorithms ready, but it took enormous calculations for that algorithm to be actually putting up a case or a good image reconstruction at that era, because computers were not available. It was out of a human's capacity to create the same thing, do all the calculations and give us a result. So he put forward the theory, and that theory was lying there for many years. So in 1956, the same theory was taken up by Bracewell, and while working with radio astronomy, so whatever rays were coming from the multiple galaxies or stars, then constructed a solar map using those X-ray projections with radon state. Further advances were made, and Mr. Oldendorf and Carmack in 1963 built first lab models individually, one in 1961 and another in 1963. They built the first model of computed tomography, but never did any clinical case on that. Actually, it was Mr. Kuhl and Edward in 1968 who successfully created a nuclear medicine scanner. They are called as fathers of PET or fathers of SPECT, and they actually created a scanner using the same theory, but it was limited to nuclear medicine only. And they were thought of making use of it to produce X-rays and then use it for body image. So all the platter was ready for making a good dish for G.N. Hounsfield. And then he made best out of it, and he created the first CAT scanner or the EMI scanner, because he was working as a senior research scientist at EMI Limited in England. So this city, the same, what we're looking at, this machine was made by G.N. Hounsfield in 1972, for which he got a Nobel Prize, and it was shared with Mr. Carmack, and then the Nobel Prize was shared between the two for the innovation and invention of best scanning modality available at that time. There is a history behind Mr. J.N. Hounsfield also. A very wonderful article I found while doing research about Hounsfield. And it was written that Mr. Hounsfield was not that excellent student in the schools, and even his teachers described him as thick, that he is not going to move around or he is not going to do anything wonderful in his life. So for many of us, it can be an inspiration, even though our teachers or even the colleague students are calling us like, you're not up to the mark, we can definitely improve even at the age of 40s and 50s. So keep improving. That was the one take-home message from the biography of Mr. Hounsfield. And another thing, he has joined the British Royal Air Force because he was not doing anything. And during World War, multiple recruitments were happening in different fields. He was not a soldier though, but he helped the pilot to navigate through the newly invented radar to the dark cloudy clouds, because he was a wizard in electrical machinery. The same thing was used by Mr. Hounsfield, and then he entered into the engineering faculty, and he got employed in EMI as a senior engineer, where he made use of all his skills, all his electrical machinery wizardry, and then he created us what we know as a CT scan or a CAT scan. So what was the principle used and the technology used by him? He used multiple X-rays projections from multiple directions to have images of particular part of a body, especially that was built for scanning the brain. So he created cross-sectional slices of the body, especially the brain, and then each image provides detailed anatomy of the body at a specific location or slice with use of these multiple projections. This was the first image created and given by him, and it has actually shown that the skull having a thick high density area, then the soft densities along the gray matter and the white matter, and a lesion which is looking different and the edema which is looking different. Till this time, it was actually perceived that Bone is the hardest part, which is having different density, and rest of the soft tissue is having water density. With this image, Hounsfield has proved that each and every part of the body has different Hounsfield units or different densities, which we can differentiate with the help of multiple projections, and hence can provide good detailed anatomy of each and every part of the body with the use of axial scanning, especially with the use of CT scanner, CAT scanner. So how do we scan? We have an X-ray source.
Did you know how much time did it take for that particular scan to happen?
Yeah, I will explain it. That will be in the next slide.
Yeah, they're great.
Yeah. So how do we do a scan? So we have a X-ray scanner, X-ray source through which X-rays are produced. It is passing through part of the body and it is detected by a detector which is at the other end of the scan. So these are aligned in such a way that whatever X-rays are produced will pass through the body and will hit a detector at the opposite end, which is exactly correlating, or it is exactly at the opposite end of the slide. So this scanning is done in the axial way, and then the scanner used to come back again. And what we used to have is a data from multiple angles, and this data is fed to a computer system. That time it must be a huge room containing all the instruments, and which constructed an image which was a filter back, only a back projection image, and that's why it has areas of blur within, and that way it was not sufficient enough to give all the details possible. But still, for that era, it must be one of the best images. So he created first generation CT scan. So we have multiple generations of CT scanners now, starting from the first generation, which was a translate rotate type, to a stationary, which was created in 1990. So these generations will revisit this chart once again, once we go through all the generations, and then we will discuss another part, why it was not used as major part of CT scanning machine as the first generation, what were the lacunae. So the first generation scanner was actually a rotate and translate type of system. I'm really grateful to Mr. Brian Nett from howradiologyworks.com, because he very generously agreed upon to use these cartoons as well as the cinema, the multiple video clips which I will be using for purpose of teaching the students. And I'm really thankful, Mr. Brian, for letting me use cartoons which you created. So this was a translate and rotate type of scanner. So what used to happen? The X-ray source used to give a pencil thin like beam, which will transmit it from source going through the body and reaching the detector. So it is scanning at one angle, say it started at 0 degrees, then it will translate to approximately 160 translation units. So first degree, 160 scans in axial view. Then another rotation of 1 degree, another 160 scans. Then another rotation in 1 degree and another 160 scans. So for one scan, it will be taking 160 scans at 1 degree. Then similar steps are repeated up to 180 scans to give enormous data which is available to us. So it took enormous time for that scanning to happen. And for one section, it was taking approximately 5 to 20 minutes to have one section of the brain to reconstruct that image. So it was big time, that 20 minutes or 5 minutes to 20 minutes for just single section of the brain, and then moving to another part and repeating the same. The slice thickness may be varying between 5 millimeters to 1 millimeter, and then again repeating the same steps for each part of the brain. So it was a lot of time, and we need to control and reduce the time to generate the images. So came the second generation. In second generation, again same pencil beam, but number of detectors have increased. Few people started with 2 detectors rather than 1, and many people, they have also reached up to 30 detectors. So the number of detectors which you are using are going to reduce the translate motion, as well as while taking the angular motion, those many angular sections will also be reduced. So what for one section, if there was a time of approximately 5 minutes, by the first generation scanner, it is significantly reduced to say around 1 to 2 minutes. But still, it's a long duration for the scan to happen. And that's why we need something faster than this. And that is why we wanted to, or source is fixed, and exactly opposite angle, multiple detectors are fixed. Now, if these detectors are placed exactly at the opposite, now both of them are rotating simultaneously in a single motion and taking multiple images and sections of the brain. So the detector is moving simultaneously with the source, and that's why it is called as rotate type of generation. And all the translate motions are now completely taken off. So there is no translate motion, only rotate motion. And that's why the image acquisition is faster, much faster than the first and second generation scanners. Now the man is mad about the speed. So whenever you are getting a faster scanning, you want to be more faster than the previous one. So we wanted to create another faster scanning. And here the concept was one thing will be moving, the source will keep on moving, and the detectors will form a ring around the source in 360 degrees rather than at angle of 50 or 60 degrees in the third generation scanner. Now what has happened? The rotation movement is still persisting, and the number of detectors have increased enormously. Initially, it used to be say around 50 or 60 detectors, or say 180 detectors. Now it must be around 180 or 200 detectors, and detectors are costly. You have to maintain them, you have to calibrate them, and you have to put them in proper positions. So it became a costly affair for the engineers, for the maintenance part, to maintain these machines and to have so many detectors, which definitely has increased the cost of the machine in all. And in addition to that, there is no significant increase in the speed of scanning or the amount of images or the quality of images what we are getting as compared to that of the third generation scanner. So if you have to pay more for same quality of imaging, definitely it is not going to be a viable option in the market. And that's why the fourth generation scanner took a backseat. Then we move to the fifth generation scanner. So both the rotatory movements of the source and the detectors are taken off. We have a good large X-ray target, which were bombarded by electron beam with magnetic deflection of the beam to cover whole body and give multiple detectors. So the electron beam is so fast and deflected so fast that it can cover complete area at a very fraction of second. So the time of acquiring images has reduced significantly by doing this, but complete geometry and complete assembly is such a costly affair that it also did not make this machine viable for many people to acquire. So now we come to the same chart again. So first generation, it was developed to show that CT can work and a body imaging can be done. It was dedicated to the anatomy of head. Similar ways, the second generation was also of the similar category, that it was dedicated for imaging of head. The first and second generation both were having translate and rotate. Definitely because of increased number of detectors, the time of acquisition of one scan has reduced from 20 minutes, 20 seconds to 2 minutes, but still it is a slower acquisition. Third generation, definitely image acquisition was fast. It is applicable to all the anatomies. So we can have a large gantry where the patient can be taken in, a table can be put in, and we can do imaging of all the parts of the body from the head to the toe. The image acquisition was faster, rather it was approximately up to 1 second. And this geometry won the prize because it was considered to be the best geometry for the modern generation city development. Still, we are using the same rotate type of scanner. The number of detectors have increased. The part or the X-ray tube which we are using has improved significantly, and we are getting better images and faster images with the third generation scanner. We have already discussed about the fourth generation scanner. It is very expensive and not good for the scatters which are happening while image acquisition, and doesn't have much advantage of speed over the third generation scanner. And the fifth generation or the other geometries what we are talking about was very good for cardiac imaging because of the temporal resolution it has, the faster imaging technique which it has, and it has low X-ray flux. But so it has low X-ray flux, and it was specific to either cardiac, and few people tried to use it with the brain imaging, but was not very successful with whole body imaging. Plus, cost was a factor. So once we went ahead with these generations, we should look at some other part of the city machine. So we know about there is a tube, then we have some filter, the flat filter, and the wedge shaped or the bow tie filter. This bow tie filter usually gives us good idea about how the body is aligned, as well as what is the shape we are scanning. What was the use of it? We will discuss in next slides to come. Then we have a beam which is passing through the patient and reaching to the detector. So X-ray tube is important. Detector assembly, the slip ring technology for faster scanning or the helical scanning is important. And then the cooling system by which the system can be cooled is important. When we talk about the CT tube, it is similar to that of an X-ray tube. It has a cathode through which electrons are bombarded on an anode, which usually is the tungsten target, and it is rotating at a higher speed so that there will be good heat dissipation from the anode, and it will go to the assembly part for the dissipation of heat, and then X-rays are produced which will pass through the body towards the detector. If you look at the cross section of this imaging, most of the recent tubes are all rotating anodes. Initially, stationary anodes were used in few earlier CT scan machines. But these rotating anodes, because of that, the heat generation and the heat dissipation capacity has increased significantly. And now we can have larger scanners or long duration scanners with the same capacity. So the focal spots were approximately 0.6. Many tubes can have two focal spots, a smaller one and a larger one. For high resolution scanning, the smaller one can be used, and the larger focal spot can be used for a normal scanning. Pulsed scanners or the tubes were used in the initial days, and most of the recent tubes are continuously X-ray producing tubes, which will produce the X-ray throughout the scanning time rather than the pulse one. And usually these tubes, they operate between the 80 to 120 kV, and MA can reach up to 1000 MA depending on the capacity of the tube or the which tube we are using. Air cooling or liquid cooling is available for both the tubes. And predominantly right now, all the tubes are cooled with the help of air-cooled systems, which are attached to the CT system. If you look at the cross-section, then we have a cathode here, then the anode, where the focal track is this, and then for heat dissipation, a copper rotating anode, copper body, which is backing up the actual anode, because copper is a good conductor of it. So whatever heat is generated along the anode track or the X-ray track will be dissipated faster to the copper, and through the rotor, it will go to the rotating anode assembly and the cooling phase. So all the assembly is a unit itself. From X-ray production to the cooling, everything has to happen within the assembly. So cooling can be air cooled or a oil which is put between the tube system, and which will allow the heat to transmit and go away as fast as possible, so that more and more X-rays can be generated. So this was the older tube with the cathode and the anode, and this was the track where all the electrons were bombarded. And this is the window through which the X-rays will come out. So the window will have a movable collimator. What was the use of this collimator? What is the use of this collimator rather? It will collimate whatever X-rays are coming out to a particular shape. This shape is very important. Initial days, it was a pencil beam shape. And now as the CT scan machines are progressing, the shape is getting wider and wider. From the pencil beam, it went to a fan beam. And then now most of the scans are using a cone beam shape. So the collimated X-rays of parallel beam, small caliper will be opened up and these X-rays will run parallel. So it will cause a parallel beam of pencil thin X-rays. The fan beam, the area has increased now, which was used initially also in the third generation scanners. So it has a long arc along the same axis, and this fan will immediately or simultaneously can pass through large part of the body and reach larger number of detectors to produce image. And nowadays the cone beam is used, so it has longer x-axis as well as the z-axis. So now it can cover large part of the body along the z-axis as well as in the x-axis and can perform the faster scanning methods. Because of faster rotation and the larger beam, we can cover the body in a faster way. So coming to from CT scan detectors were arranged in row. So approximately any scanner will have approximately 800 to 1000 detector elements along the detector arc, or we may have multiple arcs of detector which are stacked along the z-axis to give multiple slices, and this can vary from 1 to 320 to 56 and even now the flat panel. So to improve the z-axis, we have number of detectors along the z-axis, and to have good resolution, we can have number of detectors along the arc which are actually placed in an arc form, and it will be like a rectangular along the z-axis. So initially used were the xenon field ionization chambers, which was actually used up to year 2000. They have fewer ring artifacts, but they do have lower detection efficiency. So whatever X-rays are reaching up to that detector, the efficiency of those X-rays getting converted into an electric signal was only 70%. What we actually wanted to have something which is approaching 100%. So the solid state detectors were evolved. These are generally scintillators. When X-rays bombarded or X-rays reaching up to the detector, the scintillating detector will produce a light which is detected by the photodiode, and this photodiode will convert it into an electric signal, which will directly depend on how many lights or how many X-rays are bombarded or received by this scintillating detector. So if 10 X-rays are received, then the scintillating detector should convert all the 10 X-rays to 10 light photons, which will go to the photodiode, and it will then convert it into an electric signal, which will be delivered to the processing unit to make an image. So this light is converted. So what we need in addition to the scintillating detectors, that this X-ray should not cross one detector to another. So what we did, we have one anti-skate and as well as one septa, which is lying between the two detectors. So this septa cannot be much thicker because it will then reduce the area which is available for the X-rays to get on to the detector. So it has to be thin as possible, and then it should be effective also, so that X-ray should not cross from one detector to another. Similar ways, anti-scatter grids are placed just adjacent at the photodiode, so that the light should not pass from one detector to the another and should be converted to electric signal from there. So it started from one single row of detectors along the arch. Then we had two detectors. So the X-ray beam is collimated in such a way that both the detectors can be activated by a single beam and will produce two images rather than a single image. How it is going to happen? Because we have two detectors which are aligned to one another, and the X-ray is placed and collimated in such a way that it will pass through one body part, another body part. This will detect this slice, and the second detector will detect this slice, and we are getting two images from the single X-ray which is bombarded towards the body and detector. Then in 1990s, 4-slice configuration came, which had two designs. So one was equal width of detectors. So what do we have? We have say around 16 rows of 1.25 millimeter detectors. So each and every row, each and every detector will have a width of 1.25. So now whatever I do, my minimum slice or minimum area which I will be taking up will be only 1.25 millimeters. So the thickness of my slice will be just 1.25 millimeters, whatever it happens. So the Z resolution has reduced, as well as the thickness of the slice has also reduced, or will be restricted to 1.25. Now, what do we need? We need something which is below 1.25 or 1 millimeter scan to get an image which is isotropic, or which will be available for 3D reconstructions. So what they did, they made a matrix detector where multiple detectors are there, and according to your choice of thickness, what you are desiring, we can select one detector of that thickness. So if I want a thin slice of 1.25 millimeters, then I can get it by multiplying it into 4. So I can just select all these 4 detectors and get 4 slices of 1.25. But if I want a thicker slice, then I will be selecting 2 detectors at 4 parts, and it will give us a 4 slices of 2.5 millimeters. Similar ways, it can give 3.75 millimeter thickness and 4 slices of same thickness, and same ways we can have 5 slices. The scientists again innovated something else where we have variable width detector. Now this variable width detector had different thicknesses at different levels. So it started with 1 millimeter, 1.5 millimeter detector, then had 2.5 millimeter detectors, then had a 5 millimeter detectors which are placed in Z-axis. Now, if I want to scan at 0.5 millimeter, I can collimate these detectors in such a way that I will use 0.5 of this detector and 0.5 of this detector to get 2 slices of 0.5 millimeters. Similar ways, I can get 1 millimeter slices by selecting 4 detectors, half of the peripheral 2 detectors, which were actually 1.5. So 0.5 is not included in acquiring the X-rays. So only 1 millimeter of this, and the central 2 will be 1 millimeter. So I can have 4 slices of 1 millimeter each. Now I have, if I want thicker slices of 4, then I can again collimate it in such a way that I can have 4 slices of 2.5 millimeters, and then 5 millimeter slice thickness of 4. So you can just electronically choose the number of detectors, take the sample from which all these detectors has a one single unit, and you will have 4 slices of 5 millimeters. So according to your choice, you can increase or decrease the detector width and get the desired thickness of the slice. It can vary from 0.5 to 5 millimeter slice thickness, and that will help to get a sub-millimeter type of scan. So with addition to the fan beam technology and number of detectors which are increasing, from a thinner slice and a longer duration of scan, we are now approaching faster scans and even a single rotation scan for a single organ. So we can just in a single rotation can scan heart or brain to get wonderful images without significant loss of time. So we can achieve this by the different detector length and different detector rows which are added. So in multi-slice, as we have seen for 4 slices, now what we can do, we can add multiple slices of thin detectors which are assembled in such a way that we can have multiple rows, which can be of 0.5 millimeter thickness, or it can be of 0.6 to 5 millimeter thickness, to get coverage of approximately 32 millimeters in single rotation or 40 millimeters in single rotation, depending upon the thickness of the detectors in each row. So there can be stacks of say 700 or 800 detectors in an arc form, and the detector width of 0.5 or 0.625 to give us a Z axis of say 40 millimeters or 32 millimeters, leading to faster scanning. So these scanners provide excellent longitudinal spatial resolution, high quality 3D reconstruction. At the same time, it reduces the scan times. The CT scanners with up to 64 detectors row generally cover a scan volume with a helical acquisition with multiple rotations. And a 320 detector row CT scanner covers approximately 160 millimeters in one rotation, and will be helpful in cases where we want to scan hard in single rotation. In addition, then we never discussed about the bow tie filter. The bow tie filter, why it is used? See, body is not in a square or rectangular shape. It is actually a oval shaped thing. So whatever X-rays are coming from the tube, usually we consider it as a monochromatic X-rays. And all the flux of X-rays coming out of the tube can pass through the body and reach to the detector. But body is thicker at the center and thinner at the periphery. So we don't want much harder rays and number of X-rays passing through the thinner part of the body. And we want more X-rays to pass through the central part, which is thicker. So we need to provide something called as the filter, which is near the X-ray tube and will give us radiation, which will be stronger radiation and more number of X-rays at the center and lesser number of X-rays at the periphery, which is the purpose of this bow tie filter which is used. Then we usually have a flat filter just adjacent to the X-ray tube. It will make the X-ray as uniform as possible, depending on its thickness. So it is either made up of aluminum or copper, and what it makes the X-ray near to the monochromatic, like single energy photons in that way. It never happens that way, but we consider all the CT scanners to have an ideal scanner should have a monochromatic X-ray beam coming out of the tube and reaching the detector to get best possible images. Another important innovation which happened while the advancement of the machines, which actually allowed us to go from axial to helical scanning, and that is the slip ring technology. So the complete gantry is moving and we need to scan faster. So for this faster scanning, we need something which will continuously supply electricity to the tube and will continuously acquire whatever data is coming to the detector. And this was done, made possible with because of the innovation by Mr. Or Dr. Calendar et al. In 1990s. These consist of brushes that fit into the grooves to permit the current and voltage to the X-ray tubes while the tube is in continuous rotation. And we are simultaneously getting all the data from the detectors, which is passed through this brush connectors in the slip ring and will be getting converted into the signal as well as a formation of image by the computers which are available. So for faster scanning, what we require is the faster rotation, and this rotation is available, but just because of the slip ring, it is possible to scan in a continuous rotation motion. So this is an old image of the slip rings where we can see the brush ends are directly in contact with the electric supply, and then similar ways we can have images transferred from the detectors to the brush ring and to the computer directly. So now here comes the question. Most of the innovations were done by the physicists and scientists. So they must be asking, मेरे पास ट्यूब है, डिटेक्टर है, बो टाई फिल्टर है, स्लिप रिंग है, हाई वोल्टेज है, अब तुम्हारे पास क्या है? So what we actually need is मेरे पास image है. What we can have the same dialogue from Divar, famous dialogue. So मेरे पास image है, and this image is what we read. But again, it is not a simple task, and it is not a task of really a radiologist to create this image. It was again created by the physicists and the scientists. So we have to depend on those innovations. So from the hazy and the irregular grainy image, what Mr. Hounsfield has given us in 1970s, we have reached to an image where we can see a beating heart in a single section without any motion artifact. This is possible by processing these images by multiple projections. So the first generation had approximately 28,800 projections to form an image. And the present scanner, they give approximately 5 lakhs to 7 lakhs projections to form the image. Better, or the maximum the projections, better the image reconstruction will be, because we will be having n number of data, so that we will not miss on any part of that structure of the body. So these techniques for reconstructions are really helpful. What are these techniques? It started with simple back projection, then came the algebraic reconstruction, then came the iterative reconstruction, and then came the filtered back projection. The filtered back projection was actually the backbone of present day image reconstructions. Right now we have AI algorithms to start reconstructing these images, but still till now, filtered back projection is a backbone for all the image reconstructions, what we are seeing today. What happens in simple back projection? We are taking data in one image. This complete data is then transferred as a slice to what is called as sinogram data. This sinogram data will collect each and every data from all the projections in a form, in a stack, which is not related to the direction or the angle at which the scan is taken. So the detector channel will detect the images, will give the coefficient of whatever X-rays have come to it, and will form a slice or a line in the sinogram data model. This model will then reconstruct image, which is then projected as a filtered only back projection in the form of whatever linear attenuation coefficient are seen. And this is definitely going to be an hazy image. As all the voxels are now converted into pixels, what we need actually is the whatever energy is coming out from this, which is called as linear attenuation coefficient, to put the same energy into the particular box to get a wonderful image. When we try to make it by simple back projection, like whatever data is collected was taken to the sinogram stage, then to the Fourier reconstruction, and then coming back as a projected image, we will get some haziness in that image. This is a wonderful example given in the Christensen, which I love for physics. This book has really illustrated all the difficult steps very nicely. So what we can see is that one defect is made, a cross-shaped defect is made into a box. X-rays are taken, or the projections are taken from x-axis as well as the horizontal as well as the vertical axis. From the horizontal axis, we are getting this pattern, which is projected on the image like multiple shades of gray, darker at the center, and then the somewhat slightly less darker and less darker going along the periphery. This is directly proportional to the whatever X-rays are transmitting through the gap which is available. So we got one image in this X-axis, which is similar to only few bands of grays. Similar ways, the vertical projection also forms one image. Now, if we combine both these images, which is called as back projection, so we projected it backwards to form image, which is looking similar to the square, which is the deficient square in that box, and will give us some image which is looking similar to it, but not matching the same. So what we got is a hazy image by back projection, but we are not happy with this image, so we need something else. So we move to algebraic reconstruction. What is algebraic reconstruction? We will just enumerate this example by 4 boxes. So this is a say pixel with 4 pixels coming to form one image. Now I have A, B, C, D. What I have is a linear attenuation coefficient in one angle as 11, another horizontal linear attenuation coefficient of 9, another 9 here, this oblique coefficient of 7, another vertical of 10 and 8. So we can form simple equations like A plus B is 9, C plus D is 9, and we can solve this equation to get, like Sudoku, to get some numbers for all these 4 boxes. So now we know that A has linear attenuation coefficient of 3, B has linear attenuation coefficient of 6, and accordingly we can give them shades of gray. So the lighter shade for number 3 and darkest shade for number 6. This is very cute and very nicely illustrated where we have only 4 boxes. But in practical, we have n number of elements or the voxels through which the radiation or the X-ray is passing to give a resultant linear attenuation coefficient, which will be combination of all these. And to form algebraic equations of all these equations or all these linear attenuation coefficient is a Herculean task, which is even difficult for a computer to do. So what we did, we moved to iterative reconstructions. In iterative reconstruction, we consider that a best image is possible when through this organ, when we have some numbers for that particular angles. What we got is an object with these different numbers. Now we have assumed few numbers for this object, and we want to get as close as possible to that number or those object in the matrix. Here again, the same projections were carried out. In x-axis or horizontal projection, we got 9 plus 7, so 16, 1 plus 5, 6. In vertical, we got 10 and 12, and in the oblique directions, we got 8 and 14. Now we are doing calculations step by step manner. So what we did, we calculated first. So we had 16. Now we want that image to look wonderful. So what we will do, for the same 2 boxes available, we will divide the 16 by 2 to get 8 and 8. Now this will be an uniform image. For the same second row, we did the same thing. We divided 6 into 2, so we got 3 and 3. Now we calculated it in a vertical pattern, so we got numbers like 11 and 11. But the original image is giving us a number which is 10 and 12. So now we want to manipulate this number to reach this number. How are we going to do this? So we now want to reduce 1 from 11 to get to the 10. How is it possible? For 2 matrices or the 2 boxes which are available, I can subtract 0.5 from 1 and 2 to get to that number. So what I did, I subtracted 0.5 from each boxes to get 10. So what I did, 0.5 here, so 8 minus 0.5, so I got 7.5. Another 5.5 from the 3, so I got 2.5. So now it is again closer to what I wanted to get. Similar ways, I did addition of 0.5 here to get the same number, which is coming back to 8 plus 3, which is 11, 8 plus 3, so 8.5, 3.5, which is 12. So now I am getting similar numbers here, similar number here, and same ways I am now just changing those numbers to match to what I require in the oblique fraction. This completion in both axial, horizontal, and oblique pattern will be the first iterative. And we will keep on repeating the same in multiple patterns to get to the best possible image which I can achieve. This is really complex while explaining, so difficulty level must be high, and that's why we need computers to do the job, and we cannot do it. So now from the simple back projection, what we actually need is a filtered back projection to get good image, which is what we expect. So in the filtered back projection, we got multiple linear attenuation coefficient. We assigned them different squares to get to the image. From each image, we are getting a space which is called as the radon space or the sine pattern, what we got initially. This is now converted by Fourier transformation, only 1D, not 2D. So whatever image we are getting in the radon space will be transferred to a Fourier space. The characteristic of this Fourier space is that it will achieve the same angle of attenuation which was taken while taking this image. So Fourier transformation will have additional information of angle as well as information of the radon space. So now if I take image directly from here, that will be the back projection and will be an hazy image. So what I am doing here is applying a high pass filter. This high pass filter is a mathematical algorithm which will be applied to this Fourier transformation to get a Fourier transformation after putting this filter on it, which will be then back projected to get the image. So this filtered back projection needs some algorithms which will act on the radon space as well as the 2D Fourier space. And these algorithms are called as filters. The most important filter, what is usually used, is a ramp filter, which is actually a short form of Ramlack filter, which is actually an abbreviation of Ramchandra Lakshminarayan filter, devised by two Indian scientists. And this is one of the most used filter, which we called as sharp or the phone filters. Similar multiple filters can be applied to the same data to get different structures or to highlight those different structures. For example, if you use a soft tissue structure to a base data, what we are going to get is a soft tissue reconstruction predominantly. But if you use a sharp filter, you can see the difference between the image, that the structures are nicely seen, and we can see the thinner structures with a good sharpness in the image. So same data with application of different filters is going to give us a nice image or a desired image, what we require for presentation and reporting. So from a voxel, what we are getting is a pixel through filtered back projections or different reconstruction algorithms. So now each pixel has a value or a city number, which is actually an average of linear attenuation coefficient of that voxel. So a voxel has x-axis, y-axis, and a z-axis. The z-axis is going to be the thickness of the detector. So we have all the three dimensions and then an average of this linear coefficient, which is called as HU value or the Hounsfield units. Now the problem is that these HU values, according to the city number, has a limitation. So we can have multiple HU values, but 12-bit range, that is 12 to the power 2, and we get approximately 4096 shades of gray, which we can enumerate. But is it possible for a normal human eye to differentiate between these many shades of gray? It is virtually not possible. Our cells, our retina is limited with fewer numbers of grayscale identification, and it is actually having in the range of 128 or the 8 bits and rather than the 12 bits. So we cannot differentiate so many grays, so we have to limit our grays.
That's painful stuff.
Now, if we display -1000 as a black and +1000 HU value as a white, then we have little differentiation and we cannot identify the soft tissue which is available. So the HU values of different tissues or the elements which is available in the body are different. For water, it is given as 0. For air, it is -1000. For a compact bone, it is +1000. For liver, it is 60. For kidney, is 30. Fat -90, and air in lung will be -70 because it has air as well as some safety and soft tissue with it. So when we want to differentiate between these all structures, how are we going to do this? So whichever structure we want to see, we can have window length or WL for that particular structure. So for this example, if I want to see lung parenchyma nicely, I can put my window length to the lung parenchyma, which is approximately 600 -600. So I will put the window length here. Now, how many shades of gray I want to see along this window length, that I can decide by window. So if I put long window length, window width, then what I'm going to get, maximum numbers in the range will be like a white part. So whatever is there, just a window length which is available above the window length, the window widths which are available will be looking white, and the black part will be only from the lung part. So once I decide on the window length, I can decide on how many window widths I want. So that can decide what structures I wanted to see along with the lung. So I just want to concentrate on lung. I will increase my window width. So window widths to around 1600 on 1500, and that will give imaging of only lung parenchyma or air containing structures and will not give any detail about the heart or the soft tissue which is available. Now, if I want to see the soft tissue and I don't want to see the lung parenchyma, I can change the window length to a soft tissue, which will be say around 10 or minus 12 or 30, depending on the structure which I want to see, and put the window widths along it. I will put the narrow window widths so that I will have multiple grays which I can differentiate. So if you put lower window widths between, so you will have more number of grays available for identification and visualizing that structures, and so that you can differentiate between two parts of the body. So window length will be the area which you want to visualize, and that you know by knowing the Hounsfield units of those structures, and then you can adjust your window width according to how many shades of gray you want to see along that window length, and that will give us the WW or the window width. So this is an example where window length was kept at 40 for the soft tissue, say liver and the kidneys, and I need only 350 shades of gray along this 40 HU, so that most of the soft tissue densities will be evaluated nicely in one image. Similar ways, here I have taken minus 600, so air containing structures will be nicely seen, and I will not evaluate the vessels, I will not evaluate the mediastinal structures or the soft tissue to that perfection with this length, and I will only concentrate on the lung parenchyma to see these structures and evaluate it nicely. So HU values are not equal for all the machines. It is going to change from machine to machine, and even it will be changing with the tube voltage what you use. As linear attenuation coefficient of different tissues show non-linear relationship with that of water. So everything is compared with that of water. So whatever kV you use, water will have a linear correlation with increasing the kV. So the density is going to remain same. But that is not true with other soft tissues. And that's why many times what we observe, a small stone can be nicely seen when you use low kV acquisition, and it can be completely missed if you use high kV acquisition. And it is because of the non-linear relationship, and we are not going to get that particular HU at higher kV, and we will be getting the same HU at a lower kV. So this is, I think, all for now. We have reached around 50 minutes time. And in the next part, we will be dealing with spatial resolution, the temporal resolution, how table movements happen, why quarter shift or the moving anode technique is useful to evaluate faster and get more slices. We will be dealing with some higher spectrum of CT imaging like cardiac and dynamic CT imaging, and little bit of radiation dose reduction. Richa, thank you for the day.
Yeah. Excellent talk, Nilay. I think very nicely explained, very simply going slow on the physics component of it, which was very nicely explained with each and every slide. I think it's a fantastic journey. I think I started the journey of CT with this W700, with that rotate translate model.
Okay.
When we started our journey as resident doctor, then I think we were the first one in Mumbai to have a CT scanner in a teaching hospital. So there our one scan, at which is chest or abdomen, would take 30 minutes because it was saas lijiye, saas rokhiye. Scan would happen, which would be, I think, few seconds. I'm not sure what was the rotation time. And then saas chodiye. So that was a 10 millimeter cut. So as rightly Nilay had said, that era where one cut was one breath hold, whereas now it is whole body scan and one breath hold. So you see the jump. This I'm talking of 95, that era to now. So the journey was not only getting images, but making it thinner, faster. So not only the tube had to be better. For us, the challenges was the tube would get hot. I did have the option of taking thin 1 mm slices, but immediately after 5 centimeter of coverage, my tube used to heat up. So I couldn't go beyond beyond a particular level. So challenging of cooling system within the tube, a high energy tube which could tolerate the heat dissipation, which was very important. I remember we had those trunk-like things going behind the CT scanners, which were air-cooled, these CT scan tubes. The challenges were contactless rotations. I remember seeing these brushes, which very beautifully Nilay had shown, would get worn out. And during every maintenance contract, they had to change the brushes. So from a contact brush, it went to a contactless rotation. And then the challenges was such heavy data coming onto the computer, and you had to analyze it and give it in real time to the radiologist sitting here. And that's what we are doing today. We are getting real-time images, and that's what has science as the world. So Nilay, I think a fantastic journey from where Hounsfield took 30 minutes to take that image, ran for 2 hours to his EMI lab.
So you are muted.
To today's journey where we all are sitting in every nook and corner of the world and churning out the best images. Great job, Nilay, to take us through this journey of physics and history of CT. Richa, over to you.
I think Richa is busy with her reporting.
Okay. Any questions? Any questions has come up?
I think
in chat, someone had said.
Can you please repeat iterative reconstruction?
Yeah.
And
I think yes, yeah. Nilay, you can
sure
do that.
I will just go back to that slide of iterative reconstruction. So iterative reconstruction starts with the assumption that an good axial scan or a good scan has particular number of attenuation coefficients. So those are fixed and already there in the system. So when I am taking a scan of, say, chest, what I am getting is from the object, I am getting 9715. Now this object attenuation coefficient, I want to compare to the ideal scan iterative reconstruction image which I am having put in the system. So for that, now I will make few changes in these observations in such a way that my final number would be near to that of the conceived or the preformed or the fixed image what I have in the iterative reconstruction. So this is an advanced form of algebraic reconstruction. So what I did first, the first or the one iteration completes when you evaluate the axial scans, or rather the horizontal matrix, the vertical matrix, and the oblique matrix, and make images in such a way that all the data here will be near to that of the ideal image which I am having. So I am doing some iteration like 9 plus 7 is 16. So I want to make this image better by making it equal in attenuation. So I divided it into 2. So 8 and 8. So now these attenuations will be good to look at and the images will be smoother. Okay, what we are all looking after is a smooth image one and a good spatial resolution in an image. So iterative reconstructions, you must be using your iterative reconstruction in your machines right now. So 4th generation, 3rd generation iterations are available with most of the machines now. So these iterations, what they do, they make the image smooth, and then they allow us to reduce the radiation to such an extent that we can give better images with lower radiations. Why it is happening? Because of the iteration, we are taking out the noise in the image and making it smoother and smoother. So whenever you want to have sharp images, definitely lesser iterations are required because we want that image to be sharp. But when you can do it in a sharp, smoother form, then the iterative reconstruction will give us better results. Similar ways, it will also reduce the artifacts from the metal objects present in. It will reduce those strict artifacts coming out from the back projections. And that's why iteration has a application. Why it is doing so? It is making all the pixels to a uniform level. If one pixel is having very high value, for example 9, it will reduce that value to such an extent that it will come back to 8. So now 7 and 8 initially was having significant difference. Now it is having equal values. Similar ways it is doing it in horizontal. Now we add it in a horizontal vertical pattern, and we will compare it with the object's vertical calculations. So it is coming to 10 here and 12. And right now my values are coming to 11. So now I want again this value to change, and I will make it in such a way that the calculations will come in such a way that this addition will be 10, that is 7.25 and 2.5, it will be 10, 8.5 and 3.5 will be 12. So now whatever value I had, I subtracted 0.5 for 2 here. If I had 3 boxes, then I may have to subtract it in such a way that all these 3 boxes will have numbers which will be subtracted from all 3 boxes and leading to the same value. Similar ways, we will be again doing some modifications for oblique ways also. And the same values either added or subtracted to get values which is 7 plus 1, 7 plus 1 here. So this is completion of first iteration. I will again repeat the same pattern, until and unless I am getting image which are having linear attenuation coefficient, which is similar to the ideal image which is already present in the system. And that's why iteration or iterative reconstruction needs some more time, and the image reconstruction will take some bit more time than the filtered back projection on. I think that should be good for me.
But very nicely explained. It's a complicated thing, but put it up very nicely and very easy to understand.
And even someone, Devpriya, wanted to ask about back projection also. So I will just go one slide again back. So this is just a back projection, not filtered back projection. So what we have is multiple slices which are going through a part. Now the image or the acquisition is in a different angle, and the similar ways it can go to 180 degrees round. So for each and every projection, say this projection, one line is formed in a sinogram pattern. So this one line is formed and represented for single X-ray or single projection. This single projection will be added to the sinogram phase to create a sinogram, which is not giving us anything, any idea about the direction, but it is simply accumulating all the stacks of data in a sinogram. Sine, cosine we used to learn in 12th and 10th. So sine waves will give us, or can accumulate enormous data in a shorter or a smaller compact way, but it will not give us any idea about the direction. That's why if we reconstruct images from the sinogram phase, what we will be having is a hazy image. So from sinogram phase, if we really get an image that will be hazy, like example this. So we have one way X-ray stack of X-rays coming in a vertical horizontal pattern, and another stack of X-rays coming in a vertical pattern. So here one box is carved in the metal sheet, or a box in the shape of plus. So whatever X-rays are coming here will give us some image which is looking like this. So if I project on a film, what I will have maximum X-rays are coming through this because there is a vacant area here. So these X-rays will create more blackening on the film. Lesser blackening will be there at this area and further less blackening along the periphery. Similar ways, this is one projection I am getting. Another projection will be vertical projection. So this is the vertical projection. Now, if I back project these projections, one horizontal and another vertical, what I'm going to get is an image which will look like this. So this is actual representation of the plus sign here, but still I'm having haziness here also, here also. Why it is so? Because the attenuation which has happened here is projected throughout. So whatever attenuation is done here is not only limited to the central part, which is actually should be the case, but it is projected throughout the image. And that's why the back projected images will be hazy. What we do in the filter back projection, we filter the edges or the central part or the periphery or the circular central part by using different algorithms. These algorithms act in such a way that it will completely take off this box or this box or this box and will only project image from the desired area. That is why filtered back projections, all these filters, the Ramlack filter or the bone age enhancement or the lung filters, what we use are having different algorithms, and we will reconstruct those images by reducing these areas and will only project the central and the peripheral ones and give us best possible image. And that's why back projection is the backbone, but filtered back projection is the backbone of present day image reconstruction.
Thank you, Nilay. Any other questions from anyone?
Yeah,
I think you were very lucid and very beautifully. Your speed was absolutely right for these topics. Someone would think that it's slow, but no, this is that absolutely the speed which is needed for physics for someone who is new to hear it. In fact, there are some things which even I did not know. I learned because I did not go too much in the depth of physics at times, and there were some topics which I wouldn't understand, and I think you helped me to know that even now. Thank you again.
Okay. Thank you, sir.
So I think if there's no questions, do we end this session, Nilay? Is there Richa, are you there?
So next month we will be having the second part of the same session, where we will be including some advancements and touching few higher topics like cardiac CT and even the dynamic CTs, which we can do. And even we will touch few topics about reduction in the radiation dose while doing a CT scan. So good night.
Suggestion, you could start with a couple of slides with a few MCQs on these topics. Sure. It could help just refreshing first 4-5 slides, and then we can move on.
Sure.
Great. Thank you all. Thank you all attendees. Thank you faculties. Thank you, Amit. Good night to you all.
Good night. Thank you, sir.